Our next speaker is going to be Andreas Fjellstad, and the title of the talk is When Fiction Leads to Truth, the Status of Derivations in Axiomatic Systems.
Models in science. Let's see how we can apply them to axiomatic systems in logic. So, models are everywhere in sciences these days, right? I mean, in both natural and social sciences, they apply them to climate, to the economy, to language, to computation, in biology. You got models everywhere, models of all kind of, some are descriptions, some are equations, some are things made out of plastic, you know? And you do it for all kind of purposes. You predict, you explain, you teach, you just explore, you know? And all these models, they have, I mean, they are so different to another in different fields, different areas, different substances, but they always kind of like you abstract away things, you distort certain things, and you just add things that wasn't part of the phenomenon you were studying. I mean, in economy, they really like this rational agent, don't they? I mean, are there any rational agents? No, it's just something they made up to simplify things. And generally, you study your target phenomenon through this model, right? It's a way of approaching a complex phenomena in a more tractable manner. And as far as this perspective on sciences go, progress is made through better models, not discoveries of universal laws, right? Some think that model building of this kind is central to philosophy. I am more interested in my own field of research, which is logic and formal systems. And the general question that kind of driving this little presentation is it fruitful to consider formal systems as scientific models? And logic, you know, this area of research that I am engaging in, as involving model building. And some have expressed sentiments in this direction. I'm interested today in a very specific, tiny little question, very tiny question. Namely, if axiomatic systems are models of a target phenomenon, what do derivations represent? Right, it's very specific. But you gotta be specific sometimes. So I assume people have some idea about what an axiomatic system is, but some clarifications. You need a formal language. You need not just axioms, but rules of inference. You require an inductive definition of a derivation, right? You gotta know what a derivation is. And there are no assumptions. You just reason from your axioms. So most things you think about are actually not axiomatic systems. What Euclid was doing? Nope. What Peano was doing in his original paper? Nope. There are now, of course, many axiomatic systems Peano arithmetic, but that's another issue. Hilbert did not produce axiomatic systems until, well, actually he never did. It was kind of like his students who were doing that. Did Frege invent axiomatic systems? I am not a historian of philosophy or analytic philosophy, but I'm inclined to say yes, actually. But that's not the purpose of this talk. Here's a basic example, right? The intuitionistic conditional. You got two axioms. Those two, you got a rule. Here's an example of a proof. I proved a very basic fact that everything implies itself. But it requires some labor, as you can see. Nothing is for free, right? Example. Now you all know what an axiomatic system is. Assume that these are scientific models. What target phenomena do they model? What purpose can they serve with regard to that phenomena? How do they model it, right? An axiomatic system can actually just model a logic. You know, I can have an axiomatic system for first-order classical logic, but depending on what I want to prove to you about first-order classical logic, I can choose certain axioms or rules to make that proof easier, right? I can have a meta-theoretic purpose. And my vocabulary, I can just skip negation for anything but atomic formulas and kind of simplify things, fewer rules, etc. Right? It's a model for logic. You can also maybe think that, I would like to use axiomatic system to model good reasoning. Like Aristotle and his idea of logic as a tool for good reasoning. But how useful are axiomatic systems for this purpose? I mean, theorems are not, no one reasons with, if you look back at your example here, what's going on here? These are just like conditionals, embedding into conditional, embedding. No one reasons like that, right? Some might, but they don't really model good reasoning. And because they are without suppositions, and our good reasoning tend to go from assumptions, it doesn't really match on. And they are pedagogically awful. Who teaches this in their introduction course to logic? You do natural deduction because you want your students to understand the concept of deduction. And axiomatic systems are very bad for teaching the concept of deduction because the concept of deduction involves assumptions. Right. On the other hand, there is one target for which they are very useful outside of logic. And that is when you think of logic as concerning the most general truths of a domain. Here is, of course, the Euclidean tradition comes to mind. And this Euclidean method, there should be quotation marks everywhere here. The idea is something like this. You select your epistemically self-supporting truths, and then you come up with some self-evident rules of inference, and then you infer the rest of your truths, within that domain. So it's a way of organizing your knowledge. And here's the idea. By producing this axiomatization, one aims to bring to light those underlying commitments, which do not themselves require further independent support, and on which all other commitments can rest. Right? Turns out axiomatic systems are brilliant for this. The formal system to kind of model this approach to knowledge. And because what is an Euclidean proof, right? When you prove something from your axioms, you list your axioms and then you kind of pull out your theorem using the one or two inference rules you got. Well, you are transferring an epistemic status downward from the axioms, right? That's what you do. That's the whole point of it. That's why each step needs to be self-evident using the inference rule, and your axioms needs to be self-evident. Then it's not that the theorems become self-evident, but they become known because of this. And of course, historically, one can ask whether axiomatic systems were invented as formal tools for the Euclidean program. Again, I'm not a philosopher historian of analytic philosophy, so up to you. But here comes the question then. Okay, we got this picture of what this axiomatic system can model. And we know that formulas represent propositions. Those can be true or false, but if they are derivable, they are theorems, they are true. Axioms are self-evident ones. And inference rules are these kind of self-evident transitions. But what are derivations? This long list of formulas. Because was this your evidential process? Is this how you go around gathering evidence? No. Was this how you were actually reasoning? Most likely not. Most likely you were doing some kind of weird suppositional thing, and then you were, this was, the derivation does not match your reasoning, and it doesn't match your evidential process. So what is it? Here's the fun thing, or where fiction comes into mind, because I assume this is a philosophy of science conference. I can just skip this slide immediately. But hey, Bohr had a model of the hydrogen atom, and it was very useful, right? could make very nice predictions about the hydrogen atom, especially using his nice little orbits here. And, well, as Bukulish says, it's like, but these are just fictional, these orbits. I mean, according to modern quantum mechanics, there are no such orbits around the nucleus. They just like float around, these electrons. Yet, these orbits turned out to be very useful, explanatory. You could use these orbits to derive these Balmer and Rydberg formulas, and in thus kind of explain why they are the case using these orbits. But of course, the orbits are fictional because there's no way to go from these orbits into your fancy quantum mechanics. I mean, there's no path going that way. And the point I want to make is very simple, and it's that we can actually make the same point about derivations in axiomatic systems, right? They present us with something like a narrative or a computational path from the axioms to the theorems, right? Or you can look at them as this theoretical mechanism to guarantee theoremhood. And we can use a derivation. Like, once you have a derivation of a theorem from the axioms, this actually explains why the formula is a theorem, right? So this derivation has an explanatory purpose with regard to the model, to the axiomatic system as a model. So it's kind of, but they don't match anything still. Right? They don't match anything outside the system, even if they are very useful inside the model to get things going. And of course, you can start thinking, oh, but well, maybe this is part of the rest of the 2 points are basically me discussing with myself why this couldn't be the case, right? I'll just pass 2 little bullet points here. And that is that one reason not to think of as referencing anything in target phenomenon is because you can always produce different axiomatic systems for the same target phenomenon. I mean, there are going to be multiple self-evident propositions that are going to give you your truths in your domain, right? You're going to have multiple different sets of self-evident rules. So you're going to have all these kind of paths going to the same theorems. Which path do you choose? You know, And of course, just within the same axiomatic system, you're going to have infinitely many ways of proving the same theorem. Some are going to be simpler than others, some going to be shorter. But the general rule is there's no normal form. There's no like ideal way a derivation would look like inside the system because it's just a mess, these derivations. Right? So, conclusions. Yeah. Did thinking about formal systems as scientific model, did it help me to think, to gain a new perspective on axiomatics, on formal system, and particularly on this axiomatic system, right? On the use of it? I think so, yeah. I think this is, in our example here, is like, because one problem you find in the literature, contemporary literature on philosophical logic, is that there's always these complaints about, but this proof system has this little feature here. That doesn't look like anything supposed to match with whatever they are modeling, you know? Like how to make sense of these counterintuitive features. And of course, in the case of these Euclidean systems, that's the fact that derivations are of a certain kind. They don't match your good reasoning, they don't match your... But you can still provide a reason to accept it. This perspective, to look at them as scientific models. And of course, it gives you the permission to be more free in your creative endeavors to obtain formal systems that serves the right purpose for what you want to show, right? You don't always need to, all your proof systems need to look the same way, fit some kind of very narrow standards, when what matters is you're modeling a target phenomenon. You want to reach the result, you want your easy interpolation theorem, or you want decidability of first order model logic fragment of something. Well, see, that's a model. Yeah, here are the bibliography. Thank you for your attention.
Let's start from the back row. If it's okay, do we need to go first? Yes. Okay, you first. Yes.
Thank you. Yeah, you're correct. There's no one way to build a system. You can build, organize axioms in many ways and prove theorems, and it follows like if you use axioms in proving theorems, then you can organize axioms in many ways. There's several ways to organize it. Maybe one thing you didn't emphasize is that it's anyway typically problem-driven. Like it's not just like Euclid made an axiomatic system and then suddenly proved the Pythagorean theorem, but it was made for the purpose of proving the theorem. So it's actually very often I've discovered that it's the problems that guide the formulation. Like you make many versions, then you actually see that okay, this is not the correct version. I have to reformulate the axioms so that I can make like a minimal version from which I can prove the problem or the theorem.
I agree. I don't see that as contradicting what I said, even if I didn't focus on the problem-solving matters here. No, that's true. No, I agree.
Okay, let's go to the next question.
Thank you, Andy. Very interesting. About these derivations as fictions, is it a good analogy after all? Because, I mean, the most important feature of a fiction is that it is not true, but these derivations are truth-preserving. And you are right that there are many paths from the axioms to the theorems, but still, these derivations, there are true in the strictest sense. So, is the analogy, I mean, say something in defense of this derivations as fictions?
I mean, you said it yourself. They are truth-preserving, but they aren't true, right? So you can have, take your favorite Second World War movie. It's going to have a lot of truth-preserving elements to it, but it's going to be fiction nonetheless. So, but I like more to think of the path itself as the fiction, and not because are all these paths, I mean, of course you can have an ontology where all these paths end up existing, all these infinitely many paths going to each theorem. But I do find it preferable to look at them as fictions.
Looking at the time, let's just move on to the next question and continue later.
Thank you. Interesting talk. And I think you're right that there's this puzzle about what derivations would correspond to in this kind of modeling these Euclidean program. But I think it raises up a general fact about models that you shouldn't assume that everything in the model is going to be representational and represent something in the modeled. So there might not be some aspects of models rather guide us in using the model and help us to apply the model and ways of negotiating the relationship between the model and the modeled. So for instance, think about the globe. There's an equator on our globes, but there's no equator in the world, but it's just a calculation device, as Dennett pointed out, to help us in using the globe and knowing when you're halfway down. So I think derivations might be thought of as one of these entities that help us use the model rather than standing in a representational relationship to something. So you don't need to be puzzled by the fact that there are multiple paths. They're only representing the fact that it is a theorem, or they're only establishing, sorry, not representing, they're establishing for you that something is a theorem, it represents a theorem in the model. So it doesn't matter that there's more than one, or, but I was wondering, on your conclusion slide, you used the word scientific models again, and I was wondering, do you consider the Euclidean program to be an example of a scientific endeavor, and therefore the models of it are scientific models?
So I come from a field of research where the word model is a formal model, it's model theory, so it's basically an evaluation of formulas, right? So I am forced, I have this instinct, whenever I use the word model, I need to add something in front of it in these, otherwise it's so that's, I wouldn't,
Got it, that's right.
yeah. So, and I removed the word akin, which should be between as and scientific, as akin to, or something like that. Then you would kind of as analogous to. So of course, because you can look at this project as one way of aligning research methodology in philosophical logic, mathematical logic, etc., with those of the sciences. I'm not saying the other sciences because that assumes that, but as a way of aligning the research methodology here. So yeah, I'm not committed to. Yeah, but I liked your point about the equator, and seeing the line of the equator as not. So that's the way of seeing all kind of fictional elements actually as not. Of course, that's the thing. They are non-representational, but should they be? Is fiction the right word for it? I think is the real question to ask based on that.
So if you don't mind, so that's Dennett, and he got it from, I forget who, but the distinctions between abstracta and illata. So some entities are posited entities that are meant to exist, and then the other ones are merely calculation-bound entities that assist you in what. So you want to just look up.
Yeah. No. Cool, thank you.
Okay, we have one more question from the center.
Over here?
Yes, please.
Yeah.
Great catches all day long.
Thanks. I'd like to follow up on Tuukka Tanninen's question in a way, because if we are looking at proof theoretical systems, you just have to have some kind of metalogical properties. At least it must be sound and it can't be incoherent. So I was just kind of wondering, and we're talking about models and the kind of connections between proof theory and model theory come to mind, that in order to have a useful proof theory, it has to have some kind of metalogical properties like at least soundness or connections with model theory, and also into recursive function theory, that you can kind of automate these proofs and so on. How do these kind of, that there must be these kinds of connections between proof theory and model theory, and also with computation theory? How does this kind of, for the proof system to do any useful work, how do these kind of connections impact your argument that they are really fiction? Because
my favorite example against the soundness idea, your proof system always needs to be sound with regard to the logic, with regard to the models, whatever, is the use of infinitary piano arithmetic to explore finitary piano arithmetic. So the theory, the proof system you're using to explore is way stronger. You can prove the consistency of piano arithmetic in it, but you're still using it to explore piano arithmetic because it has certain like virtuous features, to use a word I heard on this conference, which is that it makes the proofs more malleable, right? So you can always go back from these, and you can always introduce, like in this case, like there's no commitment in piano arithmetic to infinitary derivations, to infinitary stuff beyond the natural numbers, the successor function. But taking on further commitments allow you to prove interesting things regarding only what piano arithmetic proves. So you can, adding stuff is okay. Also in that area. Also when you just look at different formals, when you look at just models as formal models and proof systems.
All right. With that, let's thank our speaker,